Welcome to the screencast for the second day of 3.1. The second day of 3.1 is all about exponential growth and decay. So here is the compound interest formula. If a principal P is invested at an annual interest rate R in decimal form, so that's important, you have to put it in decimal form, and it's compounded n times a year, then the balance A in the account after 2 years is given by this equation. Awesome. So let's go ahead, let's list out every single thing and what it means. P means the principal, it's how much is invested. A is going to be the balance after 2 years, so this is going to be the end balance. The R is just going to be the rate. T is the time in years. And then lastly, the N is going to be standing for the number of times it's compounded per year. So N, the number of times it's compounded per year. So if it's annually compounded, that means it's only compounded once per year, versus monthly would be 12 times a year. Daily is 365 times a year. Quarterly, well, there's 4 quarters, so it's once every 3 months, so it's 4 times. And weekly is 52, because there's 52 weeks in a year. Okay, so let's go ahead, let's try this out. So Miss Sally's invested $2,000 into an educational account for her daughter when she was an infant. The account had a 5% interest rate. If Miss Sally's does not make any other deposits or withdrawals, what will be the account balance after 18 years if the interest is compounded? A, quarterly, B, monthly, or C, daily. So let's go ahead, let's pull out important information. So this $2,000 is my P. This 5% is my rate. Don't forget, we have to write it as a decimal. T is going to be 18 years, and then quarterly, monthly and daily, these all will have certain end values. So quarterly is 4 times a year, monthly is 12, and daily is 365 times. All right, now that we've set up the problem, let's go ahead and fill in all our known values with the equation. All right, so just listing out that my principal was 2,000, my rate was 5%, I have to write it as a decimal, my time was 18 years, and the number of times it's compounded is quarterly, 4 times, and then plugging into the equation we just learned on the previous page yields $4,891.84. See if you can plug in for B and C, and then pause the video, and then you can go ahead and check. So the difference between A and B is instead of doing 4 times a year, I'm doing 12 times a year because it's going to be monthly. So I'm plugging in 12 for my N, otherwise it's the exact same thing. Notice I have like $20 more. I get $20 more by doing it every month instead of every 3 months. And lastly, if I plug into part C, so 365 times a year, so that's once a day, I'm going to have, well, let's see, it's about going to be $30 more than I originally had. $30 more to compound every single day than once every 3 months. Go ahead, pause the video if you need to see the numbers. Cool. All right, so the continuous compound interest formula. So what if it's not just every day, once a day, but constantly, every single second, every single microsecond? We're just, compounding, collecting interest, growing every single second. So this would be like an infinity number of times that we compound, right? So basically, as n goes to infinity, we are continuously compounding. It's not like, oh, we're waiting once a day, the end of the day. It's not like I'm doing it once a month or once a year, like an annual interest rate. I am instead going to, every single second, push enter. Let me see how much more interest I've gained. Let me see how much more money I've gained. Okay, so this is A per, hopefully you guys recognize this. A per is going to be continuous. If it's invested at an annual interest rate compounded continuously, then the balance A in the account after 2 years is given by A per. So for example, if we still had a $2,000 investment, still 5% interest rate, but this time instead of compiling, quarterly, maybe monthly, maybe once a day, this is going to be continuously. What will the account balance be after 18 years? So let's see. Let's list out some of our givens. This $2,000 is my P. It's going to be my principal. It's how much I'm investing. Still my 5% rate. 18 years is my T. And I believe that's all we need for a perc. All right, so let's go ahead, let's fill this in. So $2,000 times E, oops, doesn't quite look to the RT. Okay, to the rate times time, so 0.05 times 18. This is going to give me a total of $4,000, $4,919.21. Okay, so honestly, 30 more cents than if I would have compounded daily, but it's still, you know, still a lot. We're going to play a little game now. So what if she invested $3,000 instead? And what if instead of, you know, after 18 years, she waited till 20 years? So estimate, right? Kind of guess, you know, from this little experiment we've done so far, you know, $2,000 at a 5% interest rate for 18 years. You know, we see, you know, continuously compounding isn't that much more compared to what it was once every 3 months. So if I'm going to be continuously compounding the $3,000, but instead of 18 years, I do 20, is it going to be that much? We shall see. Okay, so I plug in 3,000 E to the, well, still the 5%, 20 years instead of 18. And the total I get is $8,154.85. So my point here being is the higher your original principal, the faster the stuff grows because you're collecting more and more interest. So if this was a $30,000 student loan, it would grow a lot faster than a, you know, $2,000 loan your parents waiting for you to go to college for. Okay. So in addition to investments, populations of people, animals, bacteria, amounts of radioactive decay, blah, 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 all this stuff can change at an exponential rate. The following exponential growth and decay models can apply to these situations. So exponential growth or decay. So if an initial quantity grows or decays at some exponential rate, the final amount after a time is given by the following formulas. So on the left is more or less if it's like annual versus the one on the right is continuously growing and decaying. All right, so the one on the left, let's dive in a little deeper. So this guy, I can say this is basically the same thing as y equals y naught 1 plus r all to the t, where this y is going to be my final. This y naught is my initial. Right, so we're growing if we have a rate of change higher than 0. We're decaying if our rate is less than 0. Similar here, k is just going to be your rate. It's continuous growth if it's larger than 0, say percent growing, decay if it's less than. All right, so state population is declining. Well, that's going to mean minus. It's getting smaller at a rate 2.6% annually. So if we were using the other equation, we would say, okay, n equals 1, because I'm only compounding it once a year. Here, once again, we're only going to see how much it decreases once a year. The state currently has a population of 11 million people. If the population continues to decline at this rate, predict the population of the state in 15 and 30 years. All right, so part A is the 15 years. So I'm looking for the final, right? The final population. I know my initial is 11 million. I know my time is 15 years. My rate, well, let's see, 0.026, but it's a negative because I'm declining. I can fill in all of this. It's annually, not, you know, continuous. I'm going to use the left equation. So I can plug this in. N equals 11, 1 minus 0.026 to the 15. Well, it's the same thing as saying 11 times 0.974 to the 15. Okay, so what this means is the population, right, the N, the final, is going to be about 7.4 million people. Go ahead, pause the video and see if you can solve for B. All right, well, we are using roughly the same equation. I mean, it's just instead of 15 years, I have 30. Notice that the amount I decline in the second 15 years is significantly less than the first 15 years. Right? It's kind of like I'm leveling off, right? So I'm leveling off this exponential decay. I start at a certain amount, you know, it gets smaller, but then it kind of levels off after a while. It still gets smaller, but I mean, the first 15 years I decreased way more than the next 15 years. That's my point. All right, so that's it for this lesson. Be on the lookout for 3.2.